We would like to thank Yves for the invitation and for his collaboration to these works. The title of this presentation is Design Method for Multimaterials. These studies have been carried out in I2M laboratory in Bordeaux with Hervé Warnier. At the beginning of this topic, there was the will of the designers to integrate more and more function in a single part, and which result in more requirements on a single material that sometimes can be fulfilled. So there was it was necessary to define a suitable combination of material, which we can call either multi-materials or architecture materials. Well, now the task is not anymore of choosing one material in a database, but determining several parameters, which are the component nature, the volume fraction, of each component, the architecture of the multi-materials, which means the morphology of each component, and the coupling modes, and particularly the interface. So the different studies we have carried out consist in adapting some different methods from various domains to the design of these parameters. And each of these studies was based on industrial application, which will be shown in this presentation. So first, looking at general design method, we have in green a classical method, which begins by the definition of the customer's requirement, thanks to the application. And using functional analysis, we can write a functional set of requirements. And if we know a principle of solution, we can define a material set of requirements. Then using, for example, HB's classical selection method, we can find a material for this application. In the case where there is no solution, we have to design a multi-material, which means defining all the parameters we have talked before. So this is in the blue square. It consists in defining functional mechanisms and the architecture, selecting the component, and modelizing the behavior of the multi-material. All these tasks are linked, as we can see. So in this presentation, the second and third part will describe some studies that concern the design of multi-materials, so in this blue square. But before, we're gonna see a preliminary tool that has been developed by answering the question, why designing a multi-material? So this preliminary tool is based on an analysis of the set of requirements. Often the answer to why designing a multi-material is the incompatibility of the requirements, which means that the required properties fall in a whole of material space. And this is due to the correlation between the properties that are concerned. The tools that have been developed are the first one we're not going to detail it today. It consists in the evaluation of the opportunity to find a material near the requirements, which consists in discretization of the material space and evaluation of the population of materials density around the requirements. And the other tool that has been developed consists in separating the set of requirements in two or more parts in order to separate the incompatible functions. This is the tool that I'm going to describe now. It is based on the principal component analysis method, which allows to calculate a correlation coefficient by calculating the covariance of two properties on a database. These correlation coefficients are the terms of the correlation matrix, and defining the principal axis of this matrix, which are called factorial axis, we can find an axis which minimizes the inertia of the series of points, and in our case, the points represent a material in the property space. So the interest of this method is that now, using this, we can describe a material thanks to his position on this factorial axis. So we have only one property to compare it for different constraints as shown on the graphic, which is at the bottom. When we, well, this is quite simplified, but all the materials so are characterized by their position on the axis. Two cases can happen. If we suppose we have a property P1 which has to be superior to a P10 value, and a property P2 that has to be inferior to P20 value, which is a quite simple case. There are two possibilities. The intervals can have an intersection which is not void, so this interval will characterize a population which can be solution. But in the case where there is an incompatibility between the requirements, the intersection of the two intervals is void, and this method allows us to define the distance between the two intervals, which we call the distance of incompatibility. This distance is interesting because as a function of her value, we can see if a small variation on the level criteria can allow the compatibility to be possible, or whether not. This tool has been applied to the case of a machine tool frame, which set of requirements consist in different points like static or dynamic stiffnesses, vibration damping, or thermal stability. Or for each case, we can derive a performance index. The aim of the study was to replace the reference material, which is a cast iron, having an objective of the 5% increase in performance. So the correlation matrix have been calculated for the different combination of properties for each point of the set of requirements. The correlation coefficient is generally between -1 and +1. We can see that all the terms that are near zero show that there is a low correlation, except for the value that concerns the thermal and damping performances, which seems to be correlated. So it's interesting to develop these 2 points in order to see if there is a solution. So in this case, the different criteria have been applied, and we can see that the allowable interval of value on the factorial axis is empty. So the distance of incompatibility has been calculated, and we can see that it's about 10% of the whole range of the materials, so it's quite important. So it was unnecessary to try to make an evolution in the level criteria. We wouldn't have found any solution. So this resulted in a separation of the incompatible function, which were thermal and damping functions, in two different sets of requirements. And then we proceeded a classical selection of components, which resulted in polymer concrete for this application. So in this case, we can summarize the benefits of this method by saying that we didn't detail it today, but we can study the density of materials population in the space, and in order to see that we have some opportunity to find a material to fill the required properties. We can explain the failure for a material selection, and we can then separate the different incompatible function in different sets of requirements, or we can evaluate the distance of incompatibility to see if a small variation of the criteria can benefit. So after this preliminary tool, which was on set of requirements, we're gonna see two different tools for multi-materials design. So the first one consists in a filtration method. So as we said, defining multi-materials means defining all the parameters we have already mentioned. In our case, it's the number of and variety of parameters is too important to deal with all at the same time. So we decided to have predefined parameters in order to which correspond to such a concept of solution. That's how we call this. In order to develop method to find the optimum parameters that remain free. In the first case, we're going to consider that the coupling mode is already known because we suppose the interface between the two materials, 2 or 3, is perfectly bonded. And we suppose the architecture is known. In the next example, we will consider a multi-layer material. So the remaining three parameters are constitutive materials and their volume fractions. But the selection of constitutive materials, there are classical methods in order to choose one material, but dealing with combinations of materials, we have the number of possibilities increases greatly. So it shows the necessary of a filtration before ranking the solutions. So in this case, as we know the architecture, we can find behavior models for the multi-materials. And thanks to functional requirements, we can define requirements for the multi-materials. The different steps of the filtration will consist in first search for possible materials for this to be a component, then search for possible combinations of materials, and then see in this possible combination, see if we can find possible volume fraction to fulfill all the requirements. Then we'll proceed to the ranking of the solutions. The filtration criteria are defined by the analysis of the requirements by couples. Indeed, taking the requirements by pairs, we can see that sometimes all materials can fulfill all, and that will define for us a filter. This is, we can find a very simple case when, for example, one requirement if we are looking for a part with where thickness is a free variable, we can have requirements that will need an important thickness, like having a high stiffness, for example, and some requirements that require low thickness, as for example a limited mass or cost. In this case, when we have antagonist requirements, we can define a filter. Each time we have two antagonist requirements. So the rules to search for possible component will be that to be a component, a material must fulfill at least one filter, and each filter has to be fulfilled by at least one of the components. Then this will allow, the first point will allow to define the possible materials to be some components. The second will allow to define the possible combinations of materials. Then the calculation of valuable volume fractions make another filtration on the possible combination, and will be made thanks to constraint optimization software. This tool has been developed on simple example first, and then generalized to any number of constraint and free variables. In order to illustrate that, we have applied it to an oil extraction offshore pipe. These pipes were the flow lines, which are the pipes that lie on the ground under the sea at great depth. And the set of requirements was dealing with the exploitation of extraction of oil, so when it's under the sea, but the installation too, so the transportation of the on the ship. The assumption was that the material was a multi-layer and axis symmetric. The free variable was the layer thicknesses, and the database which we used was only 62 materials, which was voluntarily reduced in order to illustrate this method. But we can see that considering only 2 components, we already had theoretically more than 3,000 possible combinations. So that shows the necessity of a filtration before ranking all the solutions in order not to evaluate all these combinations. The set of requirements has been separated in different groups. The 2 first groups were constraints that were independent from the free variable, so from the thickness, and concerned the internal and the external layer. And there was essentially a surface temperature, for example. And the third group concerned both layers and was depending on the free variable. It was about mechanical resistance, so the load that was exerted on the installation ship, and the thermal insulation, for example. The application of the method shows that first, applying the 2 first group of constraints, the number of materials, which was 62 for each layer, is now only 18 for the internal layer and 14 for the external layer, which remains in 252 combinations. Then, applying the filter as we described them in order to search for possible combinations of materials, we only had 8 combinations remaining, and then for each one, calculating the possible volume fraction to fulfill the requirements, we only have 5 combinations. So, with in this case, with simple calculations, we reduced only by filtering the database. We reduced the number of possible combinations from more than 3,000 to only 8, which is interesting in order to evaluate each solution then. And the result was that we found the classical solution, which were made of metal on the for the inside and the polymer foam outside, and found the interest of new solution developing organic matrix composite for the internal layer. Then the last tool that is presented today concerns the architecture selection. So, considering the different parameters of the multi-material, this time the coupling mode is always supposed to be perfectly bonded, but now the constitutive materials are known, and the free parameters are the architecture and the volume fraction of each component. This study, which is always under development, begins by the definition of an architecture database, which is not simple because we have to list a representative architecture with the associated models, and we have to make a hierarchy. This is a term that appeared several times today. We have to make a hierarchy, as we saw before, as a function of the different scales where the architecture is applied. So we will have macroscopic scales, for example, in our case, to have a multi-layer material, either axisymmetric or not, and then mesoscopic scale with a particular fibrous honeycomb or fins, for example, to fill these different layers. So with once this architecture database is built, we can process to the selection and comparison of architecture thanks to the component properties. This task is under development, and it will be interesting to compare very different architecture, as we saw in the illustration of the database. There are some other approaches that we will see probably today, but in our sense we are trying to compare this architecture thanks to the models that have been collected too, in order to have a first selection and then apply topology optimization in order to have a small variation on this architecture. this study is based on an application which is an electronic packaging for aerospace, which is a box that will contain an electronic board and which functions concern the protection from mechanical impact, from electromagnetic solicitation, and which must allow to the temperature of the electronic component not to be too high, so it must allow the evacuation of the heat. So concerning this study, the further development will be the simultaneous selection of materials and architecture, which will depend on the resolution algorithm that will be chosen for the architecture selection, because it will add more parameters. Then it would be interesting to consider the coupling mode, so the nature of the interface, but which is quite complex in our case, because we need to have analytical models to make the evaluation of the solutions. And the interface problem will probably make us complex behavior and taking into account problems of junction or contacts, for example. So for the moment, we didn't deal with that. Then it would be interesting too to integrate the manufacturing process in this design, in order to because it greatly influences the behavior of the multimaterials, and it's always a big problem for multimaterial. So as a conclusion, we can see that designing multimaterials deals with important number and variety of parameters, and so we have chosen some concept of solution. So we decided to define parameters in order to limit the study domain and to develop tools corresponding to each configuration, which was defined this way. All these were based on industrial case study, and this can be summarized in a structure method, which can show in which case we can use the tools that have been developed, whether if we search for components or architecture. Something we didn't talk about was the search for pre-established solution, which can be a possibility too if we have a case study database with already existing solution to a problem. Then the search for applied interface, we didn't work on this, but I think we will see tomorrow a presentation on this, which will be interesting. So thank you for your attention.